Hello students, now I am going to discuss May-June 2023 paper 42, paper 4, question number 8 and 9, 8 to 9. Let's move. Question number 8. A. Describe the difference in reactivity between chloroethane and chlorobenzene with hydroxide ion, aqueous hydroxide ion. Explain your answer. Chloroethane CH3 CH2 Cl, chloroethane, and chlorobenzene, this is chlorobenzene, so chlorobenzene is less reactive than chloroethane. Chlorobenzene is less reactive than chloroethane. Why? Because lone pair on chlorine, chlorine has lone pair, 3 lone pair. Lone pair on chlorine will overlap into the ring. This lone pair electron will go to the benzene ring and mix with delocalized electron. So this carbon-carbon chlorine carbon bond likes to double bond. So lone pair on chlorine will overlap into the ring. So CCl bond is strengthened. CCl bond becomes stronger due to partial double CCl bond. As due to delocalization, this carbon chlorine bond become double bond. So double bond is stronger, that's why chlorobenzene is less reactive. So chlorobenzene is less reactive than chloroethane because lone pair on chlorine will overlap into the ring. So CCl bond carbon chlorobenzene, in chlorobenzene this CCl bond, this bond CCl bond is strengthened. CCl bond has become strong due to partial double carbon chlorine bond. That's why chlorobenzene is less reactive. Now next one, B. Compound T, this is compound T, C5H9O2Cl is useful synthetic intermediate. Figure 8.1 shows some reaction of T. Here T reacts with excess sodium hydroxide and heat, and reaction 1, it Cl converted to CN, cyanide compound, and this compound reacts with excess hydrochloric acid and heat, and step 2 CN group converted to CH2 NH2. So first you see this. Number 2, draw the structure of W, X, Y and Z in figure 8.1. You see the answer. So when compound T reacts with excess sodium hydroxide, and first here has star group and has chlorine group. So this star hydrolysis of star by alkali. So alcohol and sodium salt of carboxylic acid will form. So here CH3, CH2, this oxygen takes hydrogen. So CH3, CH2, OH. Ethanol will be X. X is ethanol. Now W, sodium salt of carboxylic acid. So carbon oxygen double bond, and here ONA, sodium salt of carboxylic acid, and as excess sodium hydroxide. So this chlorine atom will also substitute by hydroxide ion. So hydroxy sodium salt of carboxylic acid plus ethanol is produced. Then step 1, you see chlorine goes to cyanide, nitrile compound. Then when nitrile compound and also star COO, when it reacts with excess aqueous hydrochloric acid, and hydrolysis of star is from alcohol is given here, breakdown CH3, CH2, OH, alcohol is from ethanol. Then carboxylic acids. So CO, that's OH will be added to form carboxylic acid. So carbon oxygen double bond, also OH, carboxylic acid. Then CH2, CH2, CH2 same, and CN converted to carboxyl group also. Cyanide compound or nitrile compound acid hydrolysis converted to COOH, carboxylic acid. So here two group react. One is star reaction, other is nitrile compound hydrolyzed to produce carboxylic acid. Then and this compound step 2 produces here 6 carbon, 1, 2, 3, 4, 5, 6 carbon same, hydrogen 4 hydrogen more, 4 hydrogen atom more here. So here 3, 5, 7, 9 hydrogen, but here 13 hydrogen, so 4 hydrogen will be increased. Why? Because cyanide group CN group reduce to CH2 NH2 group. So here 2 hydrogen, here 2 hydrogen, 4 hydrogen has increased in compound Z. That's why step 2, hydrolysis, reduction of nitrile compound converted to CH2 NH2, remaining CH3 CH2O CO CH2 remains same. Only cyanide ion nitrile group converted to CH2 NH2. Then next, give the systematic name for T. Give the systematic name for T. Ethyl 3-chloropropanoate. TUC name ethyl, here CH3CH2 ethyl 1 2 3. Number 3 carbon contains chlorine. Ethyl 3-chloro 1 2 3 carbon alkanoate is propanoate. So the systematic name of T will be ethyl 3-chloropropanoate. Ethyl 3-chloropropanoate. This is the one. Number 2 I already discussed. Now number 3, state the reagents and conditions for step 1 and step 2. And you see, step 1, reagent potassium cyanide condition in ethanol. So step 1, you see what happened. Step 1, this remain same, only haloalkane converted to nitrile compound, cyanide compound. So reagent will be potassium cyanide, and potassium cyanide dissolve in ethanol. Condition will be dissolve in ethanol. Next, you see number 3, state the reagents and condition for step 1, potassium cyanide in ethanol, or you can write heat. Step 2, hydrogen plus nickel, or you can write hydrogen platinum, or you can write lithium aluminum hydride, and lithium aluminum hydride reduction reaction. Step 2, you see CN group converted to CH2 and NH2. So hydrogen is added. This reaction is reduction reaction, reducing agent lithium aluminum hydride, or you can write hydrogen in presence of nickel catalyst, hydrogen plus platinum condition, lithium aluminum hydride condition in dry ether. When you use lithium aluminum hydride, condition will be dry ether. Now next, the proton means hydrogen NMR, nuclear magnetic resonance of a spectrum of T in CdCl2 deuterated chloroform. This is deuterated chloroform is solvent, is shown this diagram. Now here different environmental proton, and their which proton are responsible, and their chemical shift ppm, chemical shift unit ppm values are given. So now you are asking question, suggest why deuterated chloroform CdCl2 is used as solvent instead of chloroform for the proton NMR spectrum. And you know CdCl3 has no proton, there is no proton. So CdCl3 does not give a peak. As proton NMR there is no proton here, so it will not give any peak. But chloroform has hydrogen, so it will produce A1 peak. It will give peak. Then and complete table 8.2 for the proton NMR spectrum of T, and you see T compound is this. This is the T, this is T, this is an ester and also chlorine atom. So this is T, compound T. Now you are asking chemical shift is given 1.2, environment of proton, this means which proton gives 1.2 chemical shift, and splitting pattern means it will be doublet or triplet or quartet. Then number of hydrogen atoms responsible for this peak, which proton, the number of protons that gives this peak. You see 1.2, this is 1.2 CH3. CH3 proton is responsible for peak at chemical shift 1.2, and this will be triplet. Why? Because here CH3 there are CH2, 2 proton, so splitting pattern will be n plus 1 rule. N is the neighboring proton, so CH3 neighboring proton is 2, here 2 proton, 2 hydrogen, so 2 hydrogen plus 1, 3 hydrogen, that will be triplet. And number of hydrogen atoms responsible for this peak, here as CH3, that means number of hydrogen is 3. Then 2.8 is responsible for CH2CO, this peak. Here this is 2.8, this is CH2 and carbon oxygen double bond, this group, and splitting pattern triplet. Why? Because there are here 2 proton, here 2 hydrogen atom, so n plus 1 rule, it will be 2 plus 1, 3 peak, triplet. 3 peak is known as triplet. Number of proton responsible for this peak, here 2 proton, 2, as 1 2 bond already present, so here CH2, this CH2 means 2 hydrogen. 3.7 is this, 3.7 chemical shift is responsible for this CH2 peak. So this will also be triplet. Why? Because CH2 neighboring proton is also CH2, so 2 proton, 2 plus 1, 3 peak, triplet. And number of hydrogen atom responsible for this peak, 2 hydrogen, because CH2 means 2 hydrogen. Then 3.9 chemical shift is higher, as electronegative is atom is joined to hydrogen, chemical shift will be more. So this 3.9 is responsible for this CH2O, this 3.9. So this neighboring proton is CH3, so splitting pattern will be quartet. CH3 means 3 proton, n plus 1 rule, so it will be quartet. And number of hydrogen atom responsible for this peak, so this will be 2, because CH2. This is for environment of the photon and splitting pattern and number of hydrogen atom responsible for this peak. Next you are asking, explain the splitting pattern of the peak at 3.99. 3.99, there are 3 hydrogen on neighboring carbon. As 3.9 quartet means 4 peak, so neighboring proton is 3, that's why 3 plus 1, n plus 1 rule. So there are 3 hydrogen on neighboring carbon or on adjacent carbon, you can write. Next, number 9. Number 9, define the standard cell potential E cell. The potential difference between the two half cells under standard conditions. The potential difference between the two half cells under standard conditions. The potential difference between the two half cells under standard conditions. This is define the term standard cell potential. The potential difference between the two half cells under standard conditions is known as standard cell potential. Then number B, an electrochemical cell is set up to measure standard electrode potential of a cell consisting of iron 3, iron 2 half cell and chlorine Cl minus half cell. Draw a level diagram of this electrochemical cell. Include all necessary substances. It is not necessary to state condition used. So here right hand is positive electrode, iron 3 ion aqueous solution, iron 2 ion aqueous solution, platinum electrode. Then left hand electrode, platinum electrode and chloride ion 1 mole per dm cube solution. Chlorine gas is pass this half cell and voltmeter, 2 half cell is connected salt bridge. This is the diagram. Then number C, the cell reaction for the electrochemical cell in B is shown this: chlorine reduce and iron 2 oxidize. Standard electrode potential of this cell is given. So calculate standard Gibbs free energy in kilojoule per mole for this cell reaction. Do you know formula? Standard Gibbs free energy change equal minus NF E cell naught. So N is the number of electron. Here when chlorine goes to chloride, 2 electron, and iron goes to minus electron, then same number of electrons, so total electron will be 2. F is the Faraday constant, 96,500 coulomb, and electrode potential of this cell is given plus 0.59. So if you calculate, you get this joule per mole, then divide by 1000, you will get minus 114 kilojoule per mole. This is the standard Gibbs free energy, minus 114 kilojoule per mole. Now number D, another experiment is set up using the same electrochemical cell. In this experiment, iron 2 ion concentration is 0.15 mole per dm cube. This is not in standard condition. All other measure concentration remain at their standard values. The Nernst equation is given. So number 1, use this equation to calculate the electrode potential E for the iron half cell in this experiment, and to calculate electrode potential E of iron 3 half cell, non-standard condition E cell. So standard electrode potential of half cell is given plus 0.77, and now E cell E naught value is given and 0.059 and this 1 log this 1 this 0.15. So if you calculate, you get 0.82 volt for this equation. You can then use your answer to D1 to calculate E cell for this electrochemical cell. Use U1, then E cell you will calculate. So you can E cell 0.59 plus 0.77 and minus this, you get this value plus 0.54 volt. Or you can write it, you can solve it, reduction minus oxidation equal given plus 0.59. This is given previous question. Here 0.59. Then so reduction chlorine half cell equal this plus this, you get plus 1.36 volt. Then now E cell will be chlorine half cell plus reduction half cell minus oxidation half cell iron. So you get plus 0.54 volt. This is the answer. Thank you, dear students.